Welcome! In this session, we're tackling the problem number 1760, minimum limit of balls in a bag. This is an optimization problem that challenges us to minimize the largest number of balls in a bag after performing a given number of operations. Let's dive in and explore how to solve it step by step. In this problem, we are working with a scenario where you are given an array of integers called nums. Each element in this array represents the number of balls in a particular bag. Additionally, you are provided with an integer called max operations, which determines the maximum number of times you can perform a specific operation. The operation involves selecting any bag of balls and splitting it into two bags. The key point here is that the total number of balls across the two new bags must be equal to the number of balls in the original bag, and each new bag must contain at least one ball. The goal of the problem is to minimize the maximum number of balls in any bag after performing at most max operations. In terms of input, nums can have up to 100,000 elements, and each element as well as max operations can go as high as 1 billion. The output is a single integer that represents the smallest possible value of the largest bag after performing the allowed operations. Let's look at an example to understand this better. Suppose nums is 9, meaning there's just one bag with 9 balls, and max operations is 2. The goal is to minimize the largest number of balls in any bag. First, we can split the bag with 9 balls into two smaller bags, one containing 6 balls and the other containing 3 balls. That's one operation. Then, we take the bag with 6 balls and split it again into two bags with 3 balls each. Now, we have 3 bags, each containing 3 balls. We've used up our 2 operations, and the largest number of balls in any bag is now 3. Hence, the output for this example is 3. Now, consider another example where nums is 2, 4, 8, 2, and max operations is 4. Initially, the bags contain 2, 4, 8, and 2 balls. First, we split the bag with 8 balls into 2 bags with 4 balls each. Then, we split one of those bags with 4 balls into 2 bags with 2 balls each. We repeat this with the other bag that has 4 balls, splitting it into 2 bags with 2 balls each. At this point, all the bags contain either 2 balls or fewer, and we've used up our 4 operations. The maximum number of balls in any single bag is now 2, so the output is 2. Finally, let's look at one more example. If nums is 7, 17, and max operations is 2, the initial bags contain 7 and 17 balls. First, we split the bag with 17 balls into 2 bags, one with 7 balls and the other with 10 balls. That's our first operation. Next, we take the bag with 10 balls and split it into 2 bags, each containing 5 balls. After these 2 operations, the bags contain 7, 7, 5, and 5 balls. The largest number of balls in any bag is now 7, so the output is 7. To solve this problem efficiently, we need to consider the constraints, such as how to handle very large values of nums and max operations. For instance, if no operations are allowed, the result is simply the largest value in nums. On the other hand, if all values in nums are identical, the problem boils down to distributing the balls as evenly as possible across the allowed operations. Efficient algorithms are necessary to meet the constraints, especially since brute force approaches would be too slow for large inputs. To solve the problem of minimizing the largest number of balls in any bag after performing a given number of operations, we need to think strategically about how to split the bags. Each operation allows us to divide a bag into 2 smaller bags, redistributing the balls between them. The challenge lies in determining the smallest possible maximum size of any bag after splitting, while ensuring that the total number of splits does not exceed the allowed max operations. To approach this, we explored various strategies that balance efficiency and correctness, focusing on how to systematically break down the problem and test potential solutions. One straightforward idea is the brute force approach. Here, the intuition is to try every possible maximum value for the bags, starting from 1 and going up to the largest number in the input array, nums. For each candidate maximum value, we calculate how many splits are needed to ensure no bag exceeds this value. If the required splits surpass the allowed max operations, then that candidate value is not feasible. However, the drawback of brute force is its inefficiency. Since it involves testing a large range of values and performing calculations for each, its time complexity is proportional to the product of the array size and the largest number in the array, making it impractical for larger inputs. A more efficient alternative is binary search on the maximum value. Instead of testing each value sequentially, we use binary search to narrow down the feasible range more quickly. By focusing on the midpoint of the current range, we determine whether it is feasible based on the number of splits required. If it is, we adjust the range to search for smaller values. If not, we look at larger values. This approach reduces the number of potential candidates logarithmically, significantly improving efficiency. Ultimately, we chose the binary search approach because it offers the best balance between efficiency and correctness. The key insight here is that the number of operations needed to split a bag with B balls into groups of size at most x is mathematically determined by B1/x. This formula allows us to quickly evaluate whether a given maximum value is feasible. By leveraging binary search, we can efficiently determine the smallest possible maximum value that satisfies the problem constraints. Compared to brute force, which processes all potential maximum values, binary search drastically reduces the solution space by exploiting the monotonic nature of the problem. If a particular value is feasible, all larger values will also be feasible. This insight minimizes redundant calculations and ensures the algorithm scales well for larger inputs. While brute force is simpler conceptually, its inefficiency makes it unsuitable for this problem, especially for large arrays. Binary search, on the other hand, combines scalability and precision, making it the optimal choice for finding the solution. In this problem, we are tasked with minimizing the maximum number of balls in any bag after performing at most a given number of operations, called max operations. Each operation allows us to split a bag into two smaller bags, redistributing the balls between them. The ultimate goal is to determine the smallest possible maximum number of balls in any bag after all allowed operations are performed. To tackle this, we begin by understanding the problem and its constraints. The input is an array nums, where each element represents the number of balls in a specific bag. The challenge is to use binary search on the result, which is the possible maximum number of balls in any bag. The search space ranges from 1 to the largest value in the nums array. Binary search is suitable here because if we allow a smaller maximum number of balls, it generally requires more operations to redistribute the balls, and this relationship is monotonic. By narrowing down the search space, we can efficiently find the smallest maximum value that meets the problem's constraints. To implement this approach, we define a feasibility function that checks whether it's possible to ensure no bag exceeds a given maximum value mid after performing at most max operations. For a given value of mid, we calculate the total number of operations required. To do this, we iterate over each bag in the nums array. If a bag already has x balls less than or equal to mid, no operation is needed. However, if a bag contains more than mid balls, we calculate how many operations are needed to split the bag such that no resulting bag exceeds mid. This can be computed as x/mid, 1 if x is divisible by mid, or x/mid, otherwise. Summing up these operations for all bags gives the total number of operations required for that mid. If the total operations are less than or equal to max operations, the value of mid is feasible. Using this feasibility function, we execute binary search. We start with the range low equals 1 and high equals max, nums. At each step, we compute the midpoint mid and check its feasibility. If it's feasible, we update the upper bound high to mid to look for smaller values. If not feasible, we update the lower bound low to mid +1 to explore larger values. This process continues until low equals high, at which point we've found the smallest possible maximum value. Once the binary search concludes, the value of low represents the smallest maximum number of balls achievable after at most max operations. This is the result we return. The key insights behind this approach lie in the monotonicity of the problem. As the maximum allowable value for balls per bag decreases, the number of operations required increases in a predictable manner. This property is what allows binary search to work efficiently. Additionally, the process of splitting a bag is inherently greedy. When splitting a bag of size X into smaller bags, the goal is to distribute the balls as evenly as possible to minimize the maximum size, which in turn minimizes the operations needed. Finally, binary search optimizes the solution by narrowing down the search space logarithmically, avoiding the inefficiency of testing every possible maximum value. The algorithm relies on simple data structures, the array nums for the initial state of the bags and variables low and high to represent the binary search range. Now let's evaluate the algorithm's efficiency. The time complexity is O, n asterisk log, max, nums. This comes from the fact that for each binary search iteration, we calculate the feasibility function, which requires O, n, time to iterate through the nums array. The binary search itself performs O, log, max, nums, iterations, leading to the overall complexity. The space complexity is O, 1, as we use only a fixed number of variables, regardless of the input size. Additionally, the algorithm handles edge cases gracefully. For instance, if there's only one bag, no splitting is needed, and the result is simply the number of balls in that bag. If all bags already contain fewer balls than the threshold, no operations are required, and the algorithm directly returns the maximum value in nums. Finally, it's designed to handle large numbers efficiently, ensuring no overflow in calculations even with large values in nums or max operations. This makes the solution robust and well-suited for a wide range of inputs. This Python implementation solves LeetCode problem 1760, minimum limit of balls in a bag, using a binary search approach. The goal is to minimize the largest number of balls in any bag after a specified number of operations. The minimum size function takes two inputs, nums, a list where each element represents the number of balls in a bag, and max operations, the maximum number of operations allowed. The function defines a helper method, canDistribute, which checks if it is possible to limit the number of balls in any bag to max balls. For each bag, if the number of balls exceeds max balls, the code calculates how many splits are needed to reduce the number to max balls or below. If the total number of required operations exceeds max operations, the function returns false, otherwise, it returns true. The main function performs a binary search to find the smallest possible value of max balls. The search range starts from 1 to the maximum number of balls in any bag, max, nums. For each midpoint, mid, in the search range, the canDistribute function is called. If the current mid value is valid, i.e., the bags can be split within the allowed operations, the search narrows to smaller values by moving the right pointer to mid. Otherwise, the left pointer is moved to mid plus 1 to consider larger values. The process continues until the left pointer converges with the right pointer, at which point the smallest valid max balls value is returned. This approach ensures an efficient solution with a time complexity of O, n asterisk log, max, nums, where n is the number of bags. The binary search reduces the range of possible values logarithmically, while the loop and canDistribute processes all bags in linear time for each binary search step. Here, we start by importing the necessary Java utilities and defining the solution class. The main method of interest is minimumsize, which aims to determine the minimum possible maximum number of balls in any bag after performing at most max operations splits. To achieve this, we define a helper method, canDistribute, which takes a proposed limit max balls, the array of ball counts nums, and the maximum allowed operations. Inside this helper method, we iterate over all the bags in nums. If the number of balls in a bag exceeds max balls, we calculate how many splits are needed to reduce the number of balls per part to within the limit. This is done using the formula, balls1/max balls. If at any point the cumulative operations exceed max operations, the method returns false, indicating that the proposed limit is not feasible. Otherwise, it returns true, meaning the distribution is possible within the constraints. The main method then initializes the binary search range, setting left to 1 and right to the maximum value in nums. The binary search begins, with mid representing a candidate value for the maximum number of balls allowed in a bag. If canDistribute returns true for mid, it means this limit is feasible, so we adjust the search range by narrowing right to mid. On the other hand, if the helper method determines that the proposed limit mid is not achievable within the allowed number of operations, we adjust the search range to explore higher values by setting left to mid plus 1. The binary search continues until left equals right, at which point we have found the smallest possible maximum number of balls that satisfies the given conditions. Finally, the method returns left as the result, which represents this minimum limit. This approach ensures an efficient solution by leveraging binary search to minimize the maximum number of balls in any bag while adhering to the constraints of the problem. To begin solving this problem, let's take a simple example where we have one bag containing 9 balls, and we are allowed to perform at most 2 operations. Our goal is to minimize the maximum number of balls in any bag after performing these operations. To achieve this, we use binary search to find the minimum possible limit. We start by defining our search range. The lower bound, left, is set to 1, representing the smallest possible number of balls in a bag, and the upper bound, right, is set to the maximum number of balls in any bag, which is 9 in this case. The search will continue until the bounds converge. In the first iteration, we calculate the midpoint, mid, as 5. This represents a potential maximum limit for the number of balls in a bag. To determine if this limit is feasible, we calculate how many operations are needed to ensure no bag exceeds 5 balls. For the bag with 9 balls, dividing it into parts of size 5 requires 1 operation. Since this is within the allowed 2 operations, the limit of 5 is feasible, and we update our upper bound, right, to 5. Next, we calculate the new midpoint, mid, as 3. This represents a stricter limit for the maximum number of balls in a bag. To check if this is feasible, we again calculate the required operations. For the bag with 9 balls, dividing it into parts of size 3 requires 2 operations. This matches the maximum allowed operations, so the limit of 3 is feasible. We update our upper bound, right, to 3. Now, we calculate another midpoint, mid, as 2. This imposes an even stricter limit. For the bag with 9 balls, dividing it into parts of size 2 requires 4 operations, which exceeds the allowed limit of 2. This means a limit of 2 is not feasible, so we adjust our lower bound, left, to mid plus 1, which is 3. At this point, both bounds converge at 3, indicating that the minimum possible limit for the maximum number of balls in any bag is 3. Now, let's consider a more complex example with multiple bags, 2, 4, 8, 2, and a maximum of 4 operations allowed. Again, we use binary search to find the minimum limit. The range starts with left at 1 and right at 8, the maximum number of balls in any bag. In the first iteration, we calculate mid as 4. To determine if this limit is feasible, we calculate the operations needed for each bag. The first bag with 2 balls and the second bag with 4 balls require no operations since they already meet the limit. The third bag with 8 balls requires 1 operation to divide it into parts of size 4. The fourth bag with 2 balls requires no operations. The total operations needed are 1, which is within the allowed 4 operations. Thus, the limit of 4 is feasible, and we update the upper bound, right, to 4. Next, we calculate mid as 2. Checking this stricter limit, the first bag with 2 balls requires no operations, the second bag with 4 balls requires 1 operation, the third bag with 8 balls requires 3 operations, and the fourth bag with 2 balls requires no operations. The total operations needed are 4, which exactly matches the allowed limit. Therefore, the limit of 2 is feasible, and we update the upper bound, right, to 2. Now, we calculate mid as 1. For this limit, the first bag with 2 balls requires 1 operation, the second bag with 4 balls requires 3 operations, the third bag with 8 balls requires 7 operations, and the fourth bag with 2 balls requires 1 operation. The total operations needed are 12, which exceeds the allowed limit. Therefore, a limit of 1 is not feasible, and we adjust the lower bound, left, to mid plus 1, which is 2. At this point, the bounds converge at 2, indicating that the minimum possible limit for the maximum number of balls in any bag is 2. Let's analyze another example with 2 bags, 7, 17, and a maximum of 2 operations allowed. We initialize the search range with left at 1 and right at 17, the maximum number of balls in any bag. In the first iteration, we calculate mid as 9. To check the feasibility of this limit, we calculate the required operations for each bag. The first bag with 7 balls requires no operations, while the second bag with 17 balls requires 1 operation to divide it into parts of size 9. The total operations needed are 1, which is within the allowed limit, so the limit of 9 is feasible. We update the upper bound, right, to 9. Next, we calculate mid as 5. For this stricter limit, the first bag with 7 balls requires 1 operation, and the second bag with 17 balls requires 3 operations. The total operations needed are 4, which exceeds the allowed limit of 2. This means the limit of 5 is not feasible, so we adjust the lower bound, left, to mid plus 1, which is 6. Now, we calculate mid as 7. For this limit, the first bag with 7 balls requires no operations, and the second bag with 17 balls requires 2 operations. The total operations needed are 2, which matches the allowed limit. Therefore, the limit of 7 is feasible, and we update the upper bound, right, to 7. Finally, we calculate mid as 6. For this limit, the first bag with 7 balls requires 1 operation, and the second bag with 17 balls requires 2 operations. The total operations needed are 3, which exceeds the allowed limit of 2. This means the limit of 6 is not feasible, so we adjust the lower bound, left, to mid plus 1, which is 7. At this point, the bounds converge at 7, indicating that the minimum possible limit for the maximum number of balls in any bag is 7. To understand the time complexity of our solution, let's break it down step by step. The algorithm uses binary search to minimize the maximum number of balls allowed per bag. The binary search operates over a range that starts at 1 and goes up to the maximum value in the array nums, which we'll refer to as m. Since the binary search reduces this range by half in each iteration, it requires O log m iterations in total. Now, during each of these iterations, the algorithm calls the canDistribute function to check if the current candidate value for maxballs satisfies the constraints. Within canDistribute, we loop through all the elements in nums, where n is the size of the array. For each element, we compute the number of splits required, which is a constant time calculation. Therefore, the canDistribute function runs in O(n) time for each binary search iteration. Now, combining these two components, the overall time complexity of the algorithm is the product of the binary search iterations and the time taken by canDistribute. This gives us O(n) log m. Moving on to the space complexity, the solution uses only a small, fixed amount of extra space. Variables like left, right, mid, and operations are all simple scalars, requiring O(1) space. The canDistribute function itself doesn't allocate any additional data structures, as it processes the input array nums in place. Therefore, the auxiliary space required is constant. Additionally, since the input array is part of the problem and no extra copies are made, it does not contribute to the auxiliary space complexity. Taking this analysis further, the overall space complexity of the solution is O(1), because no extra memory is used beyond the few fixed variables we discussed. Next, let's examine the best, average, and worst case scenarios. In the best case, the optimal value of maxballs is found close to the middle of the binary search range, thereby minimizing the number of binary search iterations. However, since the asymptotic time complexity is still O(n) log m, this doesn't change the overall analysis. On the other hand, the worst case occurs when the binary search explores the entire depth of the range, performing the maximum number of iterations, log m. Even in this scenario, the canDistribute function is invoked for every candidate maxballs, and the time complexity remains O(n) log m. Thus, the efficiency of the algorithm is consistent across all cases. When comparing this approach to a brute force solution, the advantages of binary search become clear. A naive method would involve trying every possible value of maxballs from 1 to max, nums, and checking the feasibility of the distribution. This would result in a time complexity of O(m*n), where m is the largest value in nums. By contrast, the binary search optimization reduces the number of iterations dramatically, from O(m) to O log m, leading to a much faster solution. Mathematically, the binary search achieves logarithmic complexity, O log m, by having the search range at each step. The canDistribute function processes all n elements of the array during every binary search iteration, which contributes O(n). Combining these, the total time complexity becomes O(n) log m. On the space side, since no additional memory beyond a fixed set of variables is required, the space complexity stays at O(1). This makes the solution not only time efficient but also highly memory efficient, aligning well with the problem constraints. When tackling this problem, there are a few common pitfalls to watch out for. One frequent mistake is not addressing edge cases properly. For example, if max operations is 0, or if the balls in all bags are already evenly distributed, you might encounter incorrect results or even runtime errors. To prevent this, always test your solution with edge cases, such as the smallest and largest input sizes, as well as cases where no operations are required. Another issue arises when using a brute force approach for large inputs. Simply iterating through all possible splits is highly inefficient and can lead to excessive time complexity, especially if the input size or max operations is large. Instead, you should opt for a binary search strategy to efficiently find the minimum largest bag size. Lastly, it's crucial to understand the problem constraints. Many assume that splitting a bag means dividing the balls equally, but this is not required. Splits can be uneven as long as they are valid operations. Carefully reading and understanding the constraints can save you from unnecessary errors. Another frequent challenge involves incorrect calculations in the binary search process. Using low plus high /2 instead of low plus high /2 can cause issues in languages where division results in floating point numbers. This can lead to unexpected behavior, so always ensure you use integer division when calculating midpoints. Additionally, an inefficient validation function can significantly impact runtime. For example, if your validation function continues processing even after max operations has been exceeded, it will waste valuable computation time. To address this, optimize your validation function to exit early when further calculations are unnecessary, which can greatly improve performance. In an interview setting, it's important to focus on optimization. A brute force solution is unlikely to pass problems with constraints as large as 10^5, and interviewers will assess your ability to identify and implement an optimized approach like binary search. Binary search on the result is a common pattern in problems that involve minimizing or maximizing under constraints, so recognizing when to apply it is key. Also, be prepared to explain the trade-offs in your solution. For instance, binary search here offers a time complexity of O(n*log max_balls, which is much more efficient than the naive O(n)² approach. Finally, think about real-world applications when discussing your solution. This problem can be related to practical scenarios like load balancing, so connecting your approach to such use cases can demonstrate a deeper understanding. This problem shares similarities with other well-known problems that also involve binary search on the result. For example, in LeetCode 4.10, split array largest sum, the goal is to minimize the largest sum after splitting an array. In LeetCode 8.75, Cocoa eating bananas, binary search is used to find the minimum eating speed to finish all bananas within a given number of hours. Similarly, in LeetCode 1011, capacity to ship packages within D days, the task is to minimize the ship's maximum weight capacity to deliver all packages within a certain time frame. Another related problem, LeetCode 1482, minimum number of days to make M bouquets, involves minimizing the maximum number of days needed to meet a production goal. Practicing these problems can help you recognize patterns and refine your approach to binary search-based solutions. There are several approaches to solving this problem, each with its own trade-offs. The most optimal approach is binary search on the result. Here, you test candidate maximum bag sizes and calculate the number of operations required to ensure that no bag exceeds that size. While highly efficient, this method requires careful implementation of the validation function. A simpler but less effective approach is a greedy strategy, where you iteratively split the largest bag until max operations is exhausted. Although easier to implement, this approach is not scalable for larger inputs due to its high time complexity. Another option is using a priority queue or heap-based approach, where you repeatedly split the largest bag while tracking the number of operations performed. While intuitive, this method is less efficient than binary search since it doesn't directly minimize the largest bag size. Considering these trade-offs will help you determine the most appropriate approach for the given constraints. Great job! To summarize, we used binary search to solve the problem efficiently, leveraging its ability to optimize within a sorted solution space. Key takeaways include the importance of understanding constraints and when binary search is appropriate. Thanks for watching, and don't forget to like and subscribe for more coding solutions. Keep up the great work. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!